let's sort out the three surfaces you have. So the three surfaces here are the little cowboy hat looking one, right? I'm assuming you all were like looking between the tables to see what the other guys had. Is that accurate?
No.
Okay. So there's a little top hat looking one. There's a kind of funky saddly looking one. And then there's this round one that's got these kind of obvious parabolas in it that are a low spot and a high spot. So let's figure out which ones are which. Right? So we have this three functions, xy over radius squared, right?
Yes. Yeah.
And xy squared over x squared plus y to the fourth. That feels a little bit like that one, right?
Similar, but
a little different?
yeah.
And then over here we have sine of the radius squared over the radius squared, right? You guys all cool with that?
Yeah.
So which one is clearly different than the others, and which surface is it?
Mr. Hat. Top hat.
Good. The sine one, right,
Yeah.
of the radius squared only depends on the radius, right? So that's going to be the one that's symmetrical, right, in terms of angles. You guys all good with that?
Yep.
Okay, so let's talk about this one quick, because that one's the obvious one. So I'm going to go through the answer for the smiley face one. Oh, and I should plot this. Okay, so what are the contours on this thing going to look like?
Really just circles, lots of circles.
Good, lots of circles, right? Okay. Does the limit as we go to 0, 0 of this function exist?
No. It just skyrockets into infinity.
No. So you guys had this one, right?
Yeah.
So you guys thought about this as smiley face of radius and theta is sine of r squared over r squared, right? And then you guys maybe need to recall something from trig land.
Oh, okay.
So the trig thing you're recalling is that if you've got an angle r squared, right, sitting in the unit circle, where's the sine on this picture?
Up, down, vertical line.
Yeah, the sine's the opposite side, right? So this side is sine of r squared long. And then there's this other thing, which is that this arc length is also okay, so maybe you remember S is theta r from trig class.
R squared.
So this r is the radius of this circle, right?
Oh, so it's R.
The radius is 1. So the sector length is the angle. So this angle is r squared, and so the sector length is r squared too. You guys see that? As I shrink r squared, this length and this length get both smaller and closer. You guys see that? Like as we make this further and further down there, they come together, right? So sine of r squared really is about r squared. So the limit as we send sine of r squared over r squared to 0 is 1. This piece tends to 1 as r squared tends to 0.
Yeah. Okay.
So that limit does in fact exist on the little thing here,
At 1.
and it is in fact 1 high. You guys see that? Which brings us to this next question. Where are the x and y axis?
Base.
Those are on the base, right? They're just perpendicular any place on here because it's symmetrical with theta, so whatevs. Okay. Are there maxes, mins, or saddles on this thing?
No.
There's a max, there's a min.
But,
I would like to-
Sorry.
So this depends on our definitions, and I'm going to leave this to be ambiguous right now. But there's one spot that definitely looks like it has a max.
Yeah. Sorry.
That, Manya,
There's a hole there. So
there's a hole there, so it doesn't have a maximum there.
Oh, I see.
You guys all see that? Like this surface has a maximum, but the function, right, has a hole in it there, so you can't stand there. Does that make sense? So like a maximum should be a spot that you can stand on the top of a hill. But if you can't stand there, it's not a max.
You can't have, so if there's, the ridge doesn't count as a maximum point of.
Oh, good question. So the ridge, we'll talk about ridges when we get to actually defining maximums. For right now, you can think about that as a maximum, that's okay. The ridge, right? It's not a strict maximum, it's just kind of a high spot, right?
Yeah.
You guys all see that?
Yeah.
Okay. So all these little ridges and all these little valleys you can think of as like high spots. Whether they're a max or not is going to be a question once we have derivative tests.
Yeah, you didn't actually say whether or not it's a strict or.
Yeah, and I haven't told you guys what the definition of max and min are, and I'm not going to till later anyway. Cool?
Can you give us the definition of saddle?
Only that it's a spot you would stand, right, where there's
Yeah.
uphill in one direction and downhill in another.
So you've described it, you've never defined it.
Yeah, exactly.
So there's no saddles on that.
Because to write the definitions down, I need to give you partial derivatives, and we don't have them yet, so we're just kind of eyeballing stuff.
Yep.
And then we already answered that that was the cowboy hat one, right?
Yeah.
Okay, cool.
There are no mins though, right? Because it's tending towards infinity.
I mean, there are low spots, but
There's
Isn't
no
it that
global minimum
first valley
for the whole
the min?
function.
let's see. So there is a global minimum for the function. It's attained on the first valley rim,
Yeah.
or the first valley bottom.
Oh. Okay.
Because it's over r squared, so it's all tending to 0 anyway.
Yeah.
Does that make sense?
Because it gets, it,
But sign can be negative, right? So
Right.
that first value is the most negative one, or that first bottom of that trough is the most negative. But of course, it's attained in a circle, so.
Okay.
You guys all cool with that? All right, so that's smiley face taken care of. All right, so the other two I have here, right? Which one do you, let's figure out which one's right.
oh,
Okay, so let's try this. Let's set f of x and y equal to 0 for this first function, right? What do you get?
You get problems.
You get
What?
x plus y equals 0.
Yeah, so you got x over, or xy over x squared plus y squared, right? Is 0. So either x or y is 0. So this thing has zeros on x and the y axis. Cool? Okay, how about this guy? G? If I set g equal to 0, what am I going to get? Same thing. Crap, I can't use that to tell these apart. Okay, so maybe let me use something less sophisticated. I know they're both 0 on both the axes. So this is the z equals 0 contour, right? It's those two axes. Okay, so 7, what did you do? What was your reasoning?
I looked at the positive coordinates of the.
Yeah, let's just look at the signs of the coordinates, right? Like, let's do a sign test and just think. So on this guy, right? If I'm in the first quadrant, what's the sign of x and the sign of y? They're both positive, right? What's the sign of the bottom? Right? The bottom's positive always. So I got positive on the top, positive on the bottom, gives me positive. How about over here? Negative down here? Positive, negative, right? Okay, so these alternate, right? Okay, so here I have two shapes, right? Right? I'm thinking high, low, high, low. High, low, high, low. Okay, that's consistent. This one could be F. This one goes high, low,
uh-oh.
low.
Oh, okay, yeah.
You guys all see that? This one's not consistent. It can't be F. So if I had this surface, right, I'm saying, well, it's not smiley face because smiley face is symmetrical with respect to angles. And it's not F because the signs don't work out, so it must be G. So let's work with the one we know is F now. That's the third surface. You guys cool? Okay. So that's how I establish which one it is. And then drawing contours. What do the contours on this thing look like? Yeah, so I kind of have these like funky V shapes, right? You guys see that?
Yes.
Okay. Does the limit going to 0, 0 exist on this surface? No? Can you tell me where this high spot and this low spot are? I guess I've got this.
One's
Maybe
at
like
1
this?
and the other one's.
1/2, -1/2.
Yeah.
Okay, so you think they're at 1/2 and -1/2? But where are they in the domain? You guys see that? Because I know along the x and y axis this is 0, right? So I know that holding it like this doesn't work. Because those are different heights. So I gotta twist it until I find a spot where those are the same height. So that's like this. And then I might think, oh, well that goes in at 45 degrees, which I heard one of you all say. Right? So that should be y equals x and y equals minus x. And I can plug them in to figure out which height is which. You guys all see that?
One thing I noticed on that is that because the 3D printers kind of print at one height the whole time,
Yep.
they're printing level planes, so you can see the contour lines on that.
Yeah. So if you look closely at these shapes, right, the way the printer works is it prints a level and then it moves up and prints another level. So you can see the level lines on here if you look at it closely, which is actually a cool trick. So if you want to see the contour maps, right, you can just look at them from the top. And they're kind of narrower and narrower B's on this one. Okay, so does the limit exist? No, right? Because there's a way to get to 1 or 1/2 I and a way to get to -1 or -1/2, whatever it is. We established where the x's and y's are. Are there any mins, maxes, or saddles?
No saddles.
Yeah, there's kind of a high spot, right? All along the line y equals x with a hole punched in it at 0, 0 because that value is undefined. And there's kind of a low spot along y equals minus x, again with a hole punched in it at 0, 0. You guys cool with that? Is there a way I could fill in that hole to make this function continuous?
No.
Why isn't there a way I could plug this hole to make this function continuous?
Because it's that hole on x, y on all the z's.
Yeah, that limit doesn't exist, right? It would have to be plugged in that whole vertical strip, and you can't smear a point around. It wouldn't pass the vertical line test anymore, right? I'd have to fill in a whole line segment, and that's not how functions work. You guys cool with that? You could fill the hole on smiley face, right?
Yeah.
Okay, we had answered which one we've got, and the other one here, we could go through all this stuff again, but I'm sure you guys are bored enough by this. The only thing I want to talk about on this one is where are those maxes and mins? Like, where's that really low spot? Where's that really high spot?
So we figured out if you do we figured out that the y that the y and x, that those seem to be going, they're not like that. The x-axis, it's shaped as he's showing it. So we did end up doing x equals my and plugging that in, and we figured out to find those lines, we have to do then m equals y. So to do the positive one, x equals y squared. To do the negative one, x equals negative y squared.
You guys all see that? So you set this thing equal to a constant, right? And then try to figure out what the biggest constant you can make is. And these guys actually did a cool thing that computers are good at, which is to figure out what the highest z value was. They just tried some points. Like they got calculators out and each tried plugging in 4 or 5 different points, and they made a little net, right? And then they just said, well, we're getting to like 2/5, so maybe it's a half. That's actually a pretty good procedure. I wouldn't do it by hand. I would program a computer to do it, but that's actually how we do a lot of stuff. Let's see, when we're like approximating solutions to differential equations, which we're gonna do next semester if you take DEs, we just let a computer do all that crap. And the way it does it is it just picks a bunch of points and runs them around. So this is a technique that has mathematical validity. Cool? All right. That's what I wanted for that activity. Oh, does the limit exist on that one?
No, because you can get at 1/2, at -1/2, and at 0.
You guys all see that? So you can come into that level, or to that top there at on two different paths. And that's problematic. Sorry, you can come into 0, 0 and get to two different heights on two different paths.
7.
Cool? Questions, Steels?
So there are 7 points on this quiz?
Just give yourself 5 for having done the activity and throw them on the table.